Alright, welcome you guys. Today we'll be talking about geometric vectors. And geometric vectors are the easier portion for this unit of just talking about vectors and the applications and everything. Now some of you guys might have physics teachers excuse me. Some of you guys might have physics teachers that preach, oh, just use Pythagorean theorem, just do this, find the vertical and horizontal components of your vectors, and that's great and everything. But the cool thing is that in trig, in pre-calculus, you can use the law of cosines, the law of sines, and everything. But I'm getting ahead of myself. Okay. All right. So right now, geometric vectors. Vector is just a force that has magnitude and direction. Okay. So a normal vector has a magnitude. It's connotated by the absolute value bars. It's almost like the distance formula, and when you get to the algebraic portion you will be using the distance formula for some of them. Okay, and I'll show you how to do that exactly. And it has magnitude and direction, so it's a force that's going, it's pushing and it's going in a certain direction. Okay, direction is just the angle between an imaginary x-axis and the vector. So whenever you're thinking of vector, if you can imagine a windrose or a compass type object, okay, going at the origin of the actual vector, the origin point, you can actually figure out this direction right here. And you can probably draw a triangle and figure out the horizontal and vertical components as well. Practice drawing a windrose at the beginning of every vector you ever work with, because it just helps you tremendously when you're just trying to draw this stuff. Okay. Vectors made up of two components, a beginning point and a direction point. It does go on for a certain amount of direction, but usually that direction point is at the end. Okay, so let me move that Q up here. Yep, there we go. Okay, well, usually connotated by vector A. Now the actual connotation is going to be a little arrow above it. Okay, and that's not a very good arrow. That's a horrible arrow. Let me get rid of that. Okay, but it's going to be a little arrow above it. Just, it looks like a little jet from the 1960s New York Jet style. If you go look at that, go look at old school Jets logo from the NFL, and you'll be able to see what symbol goes above it. Okay, so this is just how you work with one vector. Just remember this windrose will help you out every time. Okay, now there are two ways to draw sums or differences of vectors: parallelogram or triangle. Now the parallelogram, here's our two vectors. They're both starting at the same point. Okay, and they're both going this direction and this direction. So if I were to draw a parallelogram around it, okay, I could actually draw from the beginning diagonal to the ending diagonal, or to this diagonal over here. I could actually draw that resultant vector. So when you're doing the geometric vectors, you're going to be using a straight edge or a ruler and a protractor to actually draw this stuff. Okay, so just be ready for that. I'm not a big fan of the parallelogram method. I'm a big fan of the actual method down here. This is going to be, let me continue to move it, the tail to tip method, or the triangle method. So what I do is I start out with one vector and I go till wherever direction it's going, whatever magnitude it has, and then from the end of that vector I'm going to draw the other one going in that direction. And this is where the imaginary windrose happens. So I draw a windrose here and then draw this other vector from it. Okay, and when you do that, it just makes your job a whole lot easier of trying to work with this stuff. So in other words, I would draw a really quick windrose just so I knew which direction I was going for this other resultant vector. Okay, all right, and I would just, obviously this is south of east, and this is this one right here is north of east. Okay, so I just draw those in those two spots. So in here, let me draw another one just so you guys can see it being consistent. Okay, and obviously it would represent true north and just everything that you would want in a windrose, something that's just nice. Okay, all right, now the resultant vector on this tail to tip method would be from the tail of this to the tip of the second vector. So the resultant vector would be this one right here. Okay, and so then you would have to just, actually, you would probably be going off of the original direction right here off of this. And just working with that and just seeing, oh, okay, it's this many degrees. And remember, the angle between the imaginary x-axis and the vector is what the angle you're looking for. And it also gives you direction. Okay, now scalars, the last part about geometric vectors, scalars lengthen or change the direction of the vectors, or they do both. So in other words, if I was working with something like, let's say 2p minus 1/2 q, okay, so I would take p, this p right here, let's change that to a red. Let's make it a nice red. There we go. Okay, so I would double, whoa, hello. I thought I was drawing with a straight line. I did not realize I was making my own curve. Oof. Okay, all right. So with P, I would actually have it twice the length of the original one going that direction. Okay. Now with Q, okay, Q is originally going up and to the right. Since it's negative and it's a half, it's going to be half the original length. Let me change that to blue. Okay, and I'm going to do the tail to tip method. And it's going to be going down and to the left. Okay, so that means my resultant vector, which I'm going to use purple, just for the heck of it, okay, would look like something like this. All right, and that's just how you draw it real fast and just be able to do it. Obviously, I'm freestyling it and just working with it. Okay, but you just want to be very, very, very careful when you're working with the geometric vectors and everything, that you're just following the certain method you want, or however, whatever drawing method you want, you follow it to a T. Okay, all right, so take your time, work with it, and that's it for geometric vectors. I'll talk to you later. Bye.